So this will be a solution of exercise 3 on page 196. We will not consider a more extensive treatment of chapter 5 and 6 in this week's videos. I will be uploading a short mini-series on some of the interesting things in chapter 5 and 6, where I will also kind of do the same type of treatment of this material that I've done with you guys during the exercise sessions with a brief data example. So the reason why that is not coming on video this week, even though that was originally the plan, well, has to do with brain matter and stuff like that. But that will come over the autumn holidays. So since you guys are pretty busy with advanced probability 1 at the moment anyways, I guess it doesn't make that much of a difference, fortunately. So here we will just do the solution of exercise 3. In exercise 3, we assume the so-called heterogeneity model, which is defined in definition 511 in the book, and we consider one policy. So one policy that only has one observed claim number, x. And when we say observed claim number x, then what we mean is that x is discretely distributed. So for example, we're looking at one policy. Let's just say that it's Johnny's policy. And the one observed claim number could be, for example, 3, if Johnny has had 3 car accidents and he has reported all 3 of the claims. So this is the example that we're looking at. And when we're looking at the heterogeneity model, we assume that the policies in the portfolio are independent, and each policy has a corresponding heterogeneity parameter that in some way characterizes that heterogeneity parameter that in some way characterizes that policy. And this parameter will be theta. And what we say in this exercise is we assume that given theta, x is Poisson distributed with mean value theta. So high value theta means that Johnny is a shitty driver, and a low value of theta means that Johnny is a good driver. Now, we don't know that much about theta yet because the estimator of theta will depend on data, right? However, we do note that since this is Poisson distributed, then the expected value of the number of claims for Johnny given theta will be equal to theta, since theta is the mean value in the Poisson distribution with parameter theta. What we are asked to do in this exercise, oh wait, we also have to assume that theta has continuous density. Continuous density F, subscript theta. And it lives on the positive half axis. Okay, so what we're going to do in this exercise is we wish to calculate the Base estimator. So that's one of the things that we want to do. And in order to calculate the Base estimator, we have to just write up what the Base estimator is all about. So the Base estimator is given as the mean value of mu of theta conditioned on data, which in our case is just a single data point. And this is equal to, well, if we should write it all out, then it's equal to the mean of, and mu of theta is the function that we use to denote the expected value of one x for this policy, the expected value of x given theta. And in our case, this is just equal to theta. So the Base estimator is the mean of theta given x. So just note that when they say calculate the Base estimator mean of theta given x, it isn't because the Base estimator is equal to the mean of theta. given x in general. It's just because just in this case, the thing we want to estimate, which is the mean of x given theta, it has value theta because of the Poisson distribution. Okay, so we will start doing A in the next exercise, and in order to do A, we need to just write up one lemma that will come in pretty handy. And that lemma is lemma 523. So maybe I should write it in red because it's a good lemma. So lemma 523 on page 192 in the version of the book that I have. And you can see that this lemma has two different versions, and you use the first version if x is a discrete random variable, and you use the second version if x is a continuous random variable. And essentially what we're going to do is we're going to use the lemma to find the density function of theta given x. And given that we know the density function, then we will be able to calculate the mean value of theta given x. So the lemma tells us this: if x has discrete distribution, which it has in our case because we use it to model the claim number, well then theta given x, which is the thing whose distribution we're interested in, has the following density. It has the density f theta given x equal to x. Sorry. I think they write it a bit differently in the book, so let's just use the notation in the book. I'm using Jostein's notation. So f theta of y given that x is equal to x, where they actually make these data vectors, because normally your data has more than just one observation. This is given by f theta of y, so the unconditional distribution density, multiplied by the probability that that x1 is equal to xi, where xi is the first x1, sorry, where x1 is the first data point, given that theta is equal to y, and multiplied so on until the probability that x1 is equal to xn, where xn is the last data point given that theta is equal to y. And we take all of this and divide by the probability that x is equal to x, where this x is the vector of x's and this x is the vector of data points. So the thing is that in our case, our x is just one observed claim number. So this will simplify significantly in a second when we start calculating. So see you guys in the next exercise, in the next video where we start doing A, B, and C.